Let's solve the problems on the diode equations that we have seen earlier. This problem is asking us to calculate the diode current. What is diode current? See here. So this is diode current. In the last class, we have obtained the VI characteristics of the diode. Okay, when it is forward biased, this is how it looks like, and when it is reverse biased, this is how it looks like. Okay, so IS here is called as reverse saturation current, or sometimes it is referred to as the leakage current also. And what is this VT? VT is the threshold voltage. Okay, so when this applied voltage goes beyond this threshold voltage, then only the current would start increasing. Till then, the current would be zero in forward bias also. What is this threshold voltage? Threshold voltage is the voltage that needs to be given in forward bias so that the current flows. Understand that? Okay, so in forward bias, the diode current looks like this: the exponential along with is as the amplitude. Okay, and in reverse bias, the current looks like minus is. Okay, and is, I've told you, is a very small current because it is because of the minority carriers. Okay, so it's a very small current. See here, but once the reverse bias voltage reaches a voltage called as breakdown voltage, the breakdown occurs. Okay, so we have obtained the VI characteristic considering this diode equation. Now, considering the same equation, okay, we have to find the diode current that is asked in this particular problem. So the given diode is silicon diode, and we also had talked about this eta. See here, what is this eta? Eta is 2 for silicon and is 1 for germanium. In this, we have so many other parameters, right? So K we have, then we have VD, the applied voltage, the temperature in degree kelvins. Okay, all that needs to be considered now. That's why in the problem they have given us the reverse saturation current and the operating temperature. Okay, so this operating temperature now needs to be expressed in terms of degree kelvins. It is given in terms of the degree Celsius. Okay, then then the forward bias voltage, applied is 0.6 volts. Okay, and we are asked to assume eta to be 2. For silicon diode, eta is 2, but it's advantage that they have given us this. Fine. So let's go on with this. Fine. So how the diode current is given? The diode current, everybody just take down this. The diode current is given by what? It's given by ID, right? Everybody. So it's ID. Fine. And it's ID equal to the reverse saturation current into the exponential, which is e power k Vd by Tk minus 1. I hope everybody is making the note of this, because whenever I put things on the slides here, it's better you copy it down, prepare a good notes for yourself for your reference. Fine. Now, so let's understand what all have been given. Fine. IS is given. What is IS here? IS is 10 nanoamperes, reverse saturation current. So IS is reverse saturation current. So that's given. Fine. Given. IS is given. So that's 10 nano amperes. Okay. Then TC is given. Temperature in degree Kelvin, degree Celsius is given. That's 25 degrees Celsius. Fine. So how to convert this? But this TK what you have is in degree Kelvin. So how to get that? So therefore TK can be obtained as what? Therefore TK is, yeah. Tell me.
273 plus 25.
Yeah. Take down that.
98 Kelvin.
TC plus 270 degrees Celsius. So that is 298 degree Kelvins. Yeah. So once we have TK, we can get our K also. Okay, what is that given by? It's 11,400 divided by eta. Fine, eta is given to be 2 because it is silicon semiconductor. Okay, so let's just keep it like that. Now see what's going to happen. Let's see this, everybody. Therefore, ID is given by 10 into 10 power minus 9 because it is nano, very small current because it is leakage current. Okay, then E power 11,400 divided by 2, that's K. Then VD applied voltage is 0.6 volts. Fine. Then TK, the series, this TK I'm talking about. K is 11,400 by 2. VD is 0.6, the applied voltage, and TK is the temperature in degree kelvins, that is 298. Okay. Then you can have this minus 1 or you need not have this minus 1. Can anybody comment on that? If we have this minus 1 watt, if we don't have this minus 1 watt, what difference it would make? Anybody? In which bias we have? Are we in forward bias or reverse bias? Can anybody comment on that? Seeing which parameter do we need to talk about that? Seeing VD, the applied voltage, we need to talk about that. The applied voltage is positive here, 0.6 volts. So the diode is forward biased. And when it is forward biased, I've told you this exponential is very much greater than this 1. Okay, that means this 1 can be neglected, or if you consider that also, it will not make much difference. So if you calculate this, you will have your diode current equal to 1.18 milliamps. Is that okay with you? Have you calculated this? It's fine. If you may not have time to do that, just copy it down. But after the class or some when you sit to go through these things, okay. Once you just see how to calculate this, because using the calculators is also very important. You have to learn using your calculators. Fine. Okay. Now let's go on. This is this straightforward problem. If you remember this particular equation, if you know how to deal with this K, the constant K 11,400 by eta, the applied voltage and the temperature and equilibrium. If you know how to deal with these parameters, it's straightforward substitution and obtaining the diode current. Okay. Now let's see the second problem. Everybody, copy it down. Second problem for you, everybody. See the second problem. In second problem, the forward current is given. What is forward current? What is referred to as forward current? Forward current is the current that is flowing through the PN junction diode when it is forward biased. Okay. And reverse saturation current is the current that is flowing through the diode when it is reverse biased, and it's a very small current. See, it is in milliamperes and it is in 10 power minus 14. See how small the reverse saturation current is compared to the forward current. And they have just given PN junction diode. They have not mentioned whether it is silicon diode or germanium diode, as was the case in problem number 1. See, this was silicon diode, that's why eta was 2. But here we are asked to take eta as 1. Okay, that means what the diode that we've considered is germanium. And that is not told, but they are giving us what eta is, and that's an advantage. Okay, so what is the forward bias voltage across the diode? They have given us the current. See here, in the previous round we were asked to find out the diode current or the forward current. Now we are asked to find out the forward bias. Which is the forward bias voltage here? Can you make out which is the forward bias voltage in this particular diode equation? VD, you see this VD, this is the applied voltage. If this VD is positive, it is forward bias. If this VD is negative, it is reverse bias. Okay, so when this is positive and negative, how this ID behaves, this equation ID gets manipulated, is what we had discussed in the previous class. Okay, I hoping that you remember all that. Let's move on with the solution. Okay, everybody again take down the diode equation in the solution. Okay, so what's happening here? What's given? Reverse saturation current is given, that is this. IS is given. ID is given, that is this. So here the challenge is to identify the given data. In the equation, we call this as diode current. Okay, but forward current is, what is diode current is something that you need to know. Fine. So why they are calling it as forward current? Because this is the current that would flow when this VD is positive. So what is that positive applied voltage or the forward bias voltage to have this ID as 1.5 is what they're asking us. Get that point? So how do you manipulate this particular equation to find out VD? Can you all go on now? So we are asked to get to VD. So let's first get this point. See here, ID is given. Let's identify the parameters given, because ID we call as diode current, but that itself is the forward current when VD is positive. That's given as 1.5 milliamps. Okay, IS is given, that is 2.4 into 10 power minus 14 amps. Okay, what is asked? With all this given, they're asking us what is VD, mind you. What is VD? Or the forward bias, they're very particular. The positive VD, the forward bias. Okay. Now, let's get on with this. Everybody just see. Now this is equal. Let's call this as equation number 1. Okay. So let's say when the diode is forward biased, when the diode is forward biased, VD is positive. Okay. When VD is positive, okay, what would happen to this particular exponential, everybody? This would be very much greater than -1. So that is what we're going to write now. E power k VD divided by Tk is much more greater than 1. Therefore, equation 1 implies, what does it imply? It implies that ID is just Is into e power k Vd divided by Tk, neglecting that -1. Understand this? Now, what we need to find out is this Vd. So how to deal with this? How to deal with this? So see, just see, it's just about rearranging the terms in the equation here. ID by Is e power k Vd by Tk. Now, how to get rid of this exponential? How to get this Vd out of the power? Okay, anybody? How can we find out VD now with this particular arrangement?
Log, sir, applying log.
Applying log. Very good. Which log is that?
Log
Log
to
to
the
the
base E.
log to the base E. What is that called? That is called as natural log. Or log to the base 10 is different. Okay. So taking, everybody do that, you can solve it yourselves if you're good enough. Taking natural log is log E. Okay. Log on both sides. Do that, everybody can do it yourselves. So it looks like this. They're all simple problems. Okay. This is what is going to be asked in the exam. So you can, if you're good with your basics, the things will easily fall in place. Not at all a problem. Okay. Since the natural log is there, we can bring this KVD by TK onto the left hand side, and we can have LNE. Okay. So we know that what is LNE? We know that natural log of E is 1. So this implies that natural log of ID by IS is KVD by TK. So therefore we need VD, right? Therefore VD is given by what? VD is given by TK divided by K, okay, into natural log of ID by IS. So this is how we need to rearrange the things. So what is K here? K is 11,400 by 1 because eta is given to be 1 here. See in the problem, it is given to be 1. So we need to find out all that. So where K is 11,400 by eta. Okay, eta is given to be 400. So it's 11,400, you can say. Then what else needs to be understood? What is that? TK is there, right? What is TK there? Have they given us degree Celsius or degree
300
Kelvins?
Kelvin.
They have given us 27 degrees Celsius. Okay, so TK needs to be found out also.
300.
So that's TK is equal to 27 degrees Celsius plus 273. Okay, that would give you 300 degree Kelvins. Fine. So ID is given, IS is given. Therefore, VD would be, okay, it's 300 by 11,400. Okay, natural log of 1.5 into 10 power minus 3, that is the diode forward current, divided by the reverse saturation current, which is given by this. Okay, so if you calculate this, you just copy down the answer. Okay, the forward bias voltage is given as 0.643 volts. So what is the meaning of this? If you apply this forward bias voltage, which is equal to 0.643 volts for a germanium diode, okay, then your forward current would be 1.5 milliamperes. Okay, so this is how we solve the problem. Now we will look at the equivalent circuit of the diode. So it would be more or less the same type of problems. Okay, it would all depend on how good you are in rearranging the terms so that the required parameter is found out. Okay, so it's just that. So let's stop here the problems. Uh, let's all go on with the equivalent circuit of diode. Everybody take down this equivalent circuit of diode. If a diode is there, okay, how can you realize that diode? Can you realize the diode as a short circuit, or can you realize it as what open circuit? Can we do that? Or we have to consider some other parameters of the diode also when it is forward bias, when it is reverse bias. So that is what we are going to learn here. Okay. Now, how can we go with this particular equivalent circuit? It's equivalent circuit means we are approximating the diode. Everybody understand that? We are approximating the diode. Yeah. So for approximating the diode, we approximate the VI characteristics also. See here, how was the VI characteristics here? If you see the VI characteristics, so we have exponential current here, isn't it? It is exponential. Fine. So what is happening here? It's very small here, isn't it? So let's just consider this diode in forward bias mode, and let's approximate this VI characteristics by straight lines. Understand? By straight lines, let's approximate that. So when we approximate these diode or diode VI characteristics, okay, we come across some models. Understand? So we have to see in each model how the approximation is differed. Okay, we have three such models. When we come to approximation, equivalent circuit of the diode is being obtained. Okay, so this is obtained by approximating the diode. Everybody should understand what is approximating the diode. Anybody would like to comment on that? Approximating the diode. See here, this is approximation of the diode will not be the exact replica of the diode. It is just trying to understand the diode by realizing it as an open circuit or short circuit. Understand that? So, because I've told you the diode conducts in one direction, it does not conduct in another direction. That means when would it not conduct? It would not conduct it when it is reverse bias. It would conduct when it is forward bias. So it is unidirectional. Understand? So we call diode as unidirectional divide because it allows the current to flow in only one particular direction, and that too when it is forward biased. Okay, so to understand that better, we have three models. Okay, so let's approximate the VI characteristics. Everybody just take down this. Let's approximate the diode. Let's approximate the diode by, everybody just take down that. VI characteristics by straight lines. Fine. So when we do that, we come across three models. Okay. The first model, here we have three models, three different models. Okay. The first model is model of approximations. Okay. So the first model is, everybody take down this, piecewise linear model. Piecewise linear model is the first model. I'll explain all the things here. We are approximating. If we approximate the diode, how can we represent the diode in forward bias? Okay, in terms of the resistor or the voltage is what we are going to see now, everybody. So let's consider the diode in forward bias. See here. So what we need to do to get this diode in forward bias? We have to connect the P type to the positive of the battery, N type to negative of the battery. Understand that? Now, when we do it, okay, so what all parameters would come into picture? This is VD. Okay. Now, since this is forward bias, let's call that ID as IF. The forward current. The diode current would be referred to as forward current. Fine. And you have the diode here. Fine. Understand this. We said when this diode is conducting, okay, it conducts only in one particular direction. Okay. So where do you think the diode would be conducting? The electrons would be flowing from N to P. The electrons would be flowing from N type to P type. Okay. So the diode current would be flowing in this direction. See here. This arrow marks tells you the direction of current. This is how the current is flowing. Understand that? Now, when the diode is flowing like this, okay, the current is flowing. The forward current is, when the diode is conducting, the forward current is flowing. Okay, so there the diode offers very less resistance. Instead of saying it offers no resistance, see here, practically you should understand, Practically this is not possible. What is not possible? Practically making a current zero is not possible. Understand? Or practically having the current flow uh, as a 100%, it is also not possible. That means you have a conductor, or let me just put the things in this form. Okay, if you take a resistor is not 100% perfect resistor. That means it would allow some current to flow through it. However large may be the resistance is, it will allow some current to flow through it. Okay, similarly, when the diode is conducting, it is not the perfect conductor. It would have some sort of resistance in it. Okay, and that resistance that is offered by the diode when it is forward bias is called as the forward resistance. Everybody understand this point? Okay, so when the diode is in forward bias, then also it offers some resistance. Okay, so that resistance is called as forward resistance. So that we need to consider. Forward resistance offered by the diode when the diode is forward bias, though the current is flowing. Okay, it would offer some resistance for the flow of current, and it would be very small. Okay, so that is forward resistance. And I've been telling you, see here, in forward bias you will not have current flow soon after the forward bias is applied. Understand that? Soon after the forward bias is applied, okay, you will not have current flowing. That means we don't have current flow here from zero itself. This is zero. From soon after the application, it is not happening. So this is not happening, isn't it? The current is not starting to flow at VD equal to zero. Yes. So we should understand VD should first attain this voltage VT, which is threshold voltage. So that also needs to be considered for equivalent model. Okay. So in piecewise equivalent model, we consider the diode forward current, as well as the threshold voltage of the diode. What is this? This is threshold voltage. Threshold voltage. So we need to consider this also. So understand this. We are giving you the equivalent model of the diode. So when we are doing that in piecewise linear model, we consider the diode forward resistance. Diode forward resistance and the threshold voltage. Okay. So when this VD goes beyond this threshold voltage, then only the forward current will flow. Understand that? Okay. So how does this equivalent model, how does this diode looks like? Okay, in terms of RD and VT is what we have to see. So considering RD and VT, the above circuit can be approximated, can be realized, you can say, can be realized as. Everybody see this. This is very interesting. So diode needs to be replaced. So it has to be replaced by, see here, you should take into consideration the threshold voltage and the forward resistance the diode is offering. Okay, and when it is forward biased, it is as good as a switch in on condition. Okay, switch in on condition. So that means switch in closed condition. Let me. So this is diode. It is forward bias. It is conducting. When would it conduct? When would it conduct? When it is forward bias, it would conduct. So when it is conducting, we can think this as a switch in closed condition because it is allowing the current to flow. Okay, it is acting as a switch in closed condition, but it is offering some resistance for the flow of current. That resistance is RD. And soon after the application of VT, soon after the application of VD, the current will not flow. Okay, for the current to flow, this VD has to be, okay, greater than VT. So that's why, how does this look like now? If you come to the VI characteristics, how does it look like? See here, initially it is 0. This is VD being applied. Okay, now this is IF, because it is forward biased current. So let us call this as IF in particular, not the diode current in general. Fine. So the VD when it is applied, here this VD when it is applied, this VD has to become equal to VT for this current to flow. Till this VD becomes equal to VT, the current will not flow. So that's why till this VD becomes VT. So let's see this here. This is what you need to understand. Till this VD becomes VT, okay, the forward current will not flow. Once this VD goes beyond this VT, okay, the forward current will start flowing. But since it is piecewise linear model, we approximate it by having the straight line. Everybody understand that? Okay, now you have some slope here. You have some slope. What is slope of the line? Let me give you. What is slope of this line? Here, this is delta IF. Okay, this is delta VD. What is slope now? Can anybody tell me? What is slope? Slope is, yes,
Delta IF by
yeah, it's y
delta
by
VD.
x, y by x. That means it is delta IF by delta VD. And this slope tells us that we are considering the forward resistance of the diode also. Okay. Therefore, where this RD is delta IF by delta VD. So because of the RD, the resistance considered here, okay, we approximate the line through a slope. Because of this RD, this line has got a slope, and because of the VT considered, the diode, the forward current is flowing only after this VD reaches VT. Understand that? So this is what is called as linear piecewise model. In piecewise linear model, okay, we consider the diode forward resistance as well as the threshold voltage of the diode. Okay, you should understand diode forward, this diode forward resistance is the resistance that is offered by the diode when it is forward bias. It is very less, but we have to consider that. When we consider, okay, we will have this slope. We will have this slope. What if it is not considered? That we shall see in some other model, in the next model to come. Okay, so in piecewise linear model, since we are considering RD, we need to give this slope. There are two more such models. Okay, there are two more models. One is called as the approximate model, the other one is called as the ideal model. Let's see those two models in the coming class. Okay, as of now, let's just understand what is piecewise linear model. In piecewise linear model, okay, we consider the diode forward resistance as well as the diode threshold voltage, which is the voltage which needs to be attained for flow of current when it is forward biased.